Hey everyone, welcome back to the series. Today we're taking a deep dive into something really important for bare metal and low-level embedded work, the linker script. If you watched the last video, we built a minimal startup file for the 873X80 ARM Cortex-M3 microcontroller, the heart of the Arduino Due, and started using symbols like _SData, _EData, _SPSS, _EBSS, and _EStack. You already know these symbols come from the linker script, and in this video, we're going to build that linker script step by step and understand exactly what each line does. But first, what is a linker, and why do we even need a linker script? After compilation, our C files turn into object files. The linker's job is to take all those object files, combine them together, and decide where everything lives in memory: flash, SRAM, stack, or heap. In embedded systems, we don't have an operating system doing that for us. We have to describe the memory layout ourselves, and that's exactly what the linker script is for. Alright, let's get started. Create a file and name it sam3x80.ld. And the very first thing we do is specify the entry point of our program, the function where execution begins after reset. And here we say entry, and we pass in reset _handler. Next, we define the memory layout of our microcontroller using the memory block. Memory. This tells the linker I'm about to describe all the memory regions that exist on this device. And here's the first one. Flash, inside parenthesis, RX, origin equals this address, length equals 512K. Flash is simply the name of this memory region, and this is where our program code lives. RX defines the access permissions for this memory region. R means readable, X means executable. We don't normally write to it at runtime. Origin specifies the starting address, and length is the size. Next, we'll define the SRAM region, where our variables stack and heap will live. SRAM, parenthesis, RWX, origin equals this address, length equals 96. The access permissions here are RWX, R for readable, W for writable, and X for executable. Then we define the top of the stack, _E stack equals origin, and we pass in SRAM plus length. Again, we pass in SRAM. _E stack is the address the CPU will load into the stack pointer on reset. Origin SRAM gives us starting address of the SRAM region, and length SRAM gives us the total size of SRAM, which is 96 kilobytes in our case. When we add these together, we get the address just past the end of SRAM, effectively the top of the SRAM region. Since the stack grows downward on ARM Cortex-M, this is the correct address to use as the initial stack pointer. Now we move on to the sections block. Sections. Inside this block, we tell the linker how to organize our program in memory. The first section we define is the interrupt vector table. .isr _vector origin, and we pass in flash. And we have a colon here. The vector table is located at the start of the flash memory. Then we say keep inside parenthesis asterisk inside parenthesis .isr _vector. This tells the linker to include all the sections named .isr_vector from all object files. The asterisk means from any object file, so no matter which source file defines the vector table, it will be pulled in here. Now the important part is the keep keyword. Normally, the linker performs garbage collection and removes any sections that appear to be unused. Even though we define the vector table in our startup.c file, we never actually read from or use that array anywhere else in our code. So without keep, the linker might think this section is unused and remove it, which would completely break the program. So keep tells the linker, no matter what, do not discard this section. And we close this section and tell the linker where it should live. Next, we define the .text section. .text. And the .text section contains the main program code, all our compiled instructions. The first thing we do inside this section is align the location counter. Dot equals align 4. The dot here is a special symbol in the linker script. It represents the current location counter. It's the address where the next data will be placed. Its value depends on where the section will be placed in memory, and dot tracks the current address inside that section. Align 4 tells the linker to move that address forward if necessary, so it's aligned to a 4-byte boundary. On an ARM Cortex-M3, instructions and most data are naturally aligned to a 32-byte boundaries, so 4-byte alignment ensures safe and efficient memory access. If the current address is already aligned, nothing changes. But if it isn't, the linker inserts padding bytes until it reaches the next 4-byte boundary. Then we say asterisk inside parenthesis .text asterisk. This line tells the linker to collect every section whose name starts with .text from all object files that are being linked. For example, object files may contain sections like .text, .text.main, or .text.reset_handler. So the first asterisk means from all object files, and the second one means every section whose name starts with .text. Next, we include the read-only data used by our program. Asterisk inside parenthesis .rodata asterisk. Then we align the location counter. That equals align, and we pass in 4. .rodata stands for read-only data. This section contains constants such as string literals, const variables, and lookup tables that never change at runtime. Now we mark the end of .text section. _eText equals dot, and we place it in the flash memory region. Next, we define the .data section. This is where all our initialized global and static variables go. Things like, for example, int counter equals 42 or char msg equals hello. Here we say .data colon, and we place this section into SRAM. This tells the linker at runtime these variables must live in SRAM, which means they are fast and writable. But here's the problem. If we only store them in SRAM, all the initial values like 42 or hello would disappear when power is lost. That's because SRAM is volatile memory. On the other hand, if we only store them in flash, we cannot update them during normal program execution because writing to flash requires special erase-write operations. So what we really need is both at the same time. Initial values stored safely in flash and writable copy in SRAM during runtime. To solve this, here we write at inside parenthesis _eText. This tells the linker store the initial values of that data in flash right after the code and constants end, which is where _eText points. Inside this section, first we align the location counter. That equals align and we pass in 4. And we define the starting point of our initialized variables in SRAM. Underscore S data equals dot. Since the dot data section is placed in SRAM, underscore S data becomes the starting address where the initialized variables will live at runtime after we copy them from flash. And we actually implemented that copy operation in the previous video when we built startup.c. Now we place all the actual initialized variables from our source code. Asterisk, parenthesis, dot data, asterisk. And we align the location counter again. Dot equals align 4. After that, we mark the end of the dot data section. Underscore E data equals dot. Now we define underscore SI data equals load ADDR, and we pass in dot data. Underscore SI data points the start of the dot data section in flash, where the initial values of our variables are stored. Remember, the dot data section lives in SRAM at runtime, but its initial values are in flash. And underscore SI data tells the startup code where to copy them from. Now we define the .bss section. .bss no load. The .bss section is where all uninitialized global and static variables live. For example, int counter without an initial value. The no-load attribute tells the linker, do not store any initial values for this section in the binary, just reserve space in SRAM. That's because uninitialized variables don't need to be copied from flash, they just need a block of zeroed memory at runtime. In the previous video, our startup code zeroes out the .bss section at startup, so all these variables start with a value of 0. We start this section with dot equals align 4 and marking its beginning underscore SBSS equals dot. Next, we include all the .bss variables from our object files. Asterisk inside parentheses .bss asterisk. And we also include any common symbols. These are variables that the compiler declared without the section. And here we say asterisk common. And that equals align 4. Finally, we mark the end of the section. Underscore EBSS equals dot. And we place it in SRAM. That's it for our deep dive into the linker script. In the next video, we're going to compile our code, both blink.c and startup.c, create a makefile and upload it to the board. And finally, we'll see if the LED actually blinks on our Arduino Due. So make sure to hit that subscribe button and turn on notifications so you don't miss it. Thanks for watching.